In this video, we are going to discuss about dynamic CMOS logic. So, what are the logic which comes under this dynamic CMOS logic is first one is domino logic, NORA logic. NORA means no race logic, okay, or NP logic. Then zipper logic. Okay, so this dynamic CMOS logic, it depends on the temporary storage of charge in a parasitic load capacitance. Instead of relying on steady state behavior. So this will comes under non-ratioed logic. Okay. So here it consists of n. N is a number of input plus 2 transistor. Okay. So if you see this case, this is nothing but y is equal to whenever the clock is 0. Okay, whenever the clock is 0, it will enter into pre-discharge phase. That is, this PMOS is active. PMOS is on. Okay, PMOS is on. Okay, whenever the clock is 0, so the VDD will reach this load capacitance. Okay, so I can write y is equal to clock bar. Okay, plus whenever the clock is 1. Okay, whenever the clock is 1, and if the NMOS logic, that is A, B, C is 1, okay, this output goes to ground. Okay, so I can write this as A, B, C, the whole bar into clock. Okay, that is the output goes to 0. Perfect. So if I consider my during this is a pre-charge phase, okay, and this one is a evolution phase. This is for clock. Okay, when clock is 0, my output goes to 1, right? My output goes to 1. Okay, suppose if I connected only A. Okay, so what will happen? This is nothing but A bar. A bar only I should get, right? So consider this A is okay. Then okay, sorry, I can draw it like this. Okay, this is 0, so the transition like this. Okay, so my y is 1, since this is up to this one is a pre-charge phase, so that is 1. Okay, so after that I must get the inverse of this one, right? So this becomes 1, and 0 and 1, then it goes to 1. Okay, so this is what I should get. But if you see, whenever the clock is 0, it goes to so what I should get, actual y. Okay, actual y. So whenever the clock is 0, the output is 1. Okay, so after that y is 0. So since a is 0, it will not active, so it will remain in 1. Okay, whenever this it goes to 0 only, as it goes to 1 only, it will conduct. So my output goes to 0 and it will remain 0 till this evaluation phase, right? After that it will goes to 1. Okay, so instead of getting this output, I am getting the actual output as this one. Okay, so you can see there is a issue in designing the dynamic CMOS logic. So in order to avoid this problem, it has to, if suppose if you see the A is going to 1, it has to make only one transition. Okay, and it will remain in the same state. Okay, this is my A. So if you see what will be my actual output, so it will be 1. Okay, till this one. Okay, till this one, and it goes to 1. So suddenly it will goes to 0. Okay, suddenly it goes to 0 and it will remain in 0. Okay, it will remain in 0 for remaining 0 for entire evaluation phase, and again it will goes to 1. So these are the problems in the dynamic CMOS logic. So this can be avoided by making only one transition in the A. Okay, so you can see during the pre-charge phase, the output goes to 0, output goes to 1, and during the evaluation phase, if N conducts, means the output goes to ground. Okay, otherwise it will remains in the high impedance state. Okay. So during the evaluation phase, if the CMOS conduct, then my Y goes to 0. Okay. See, if MMOS not conduct, okay, if MMOS not conduct means Y remains in the high impedance state. High impedance state. Okay. So once if the charge get discharged, okay, till it has to wait for the pre-charge phase not to charge this value. Okay, so you can see it consumes a dynamic power. Okay, and this dynamic power is so it consumes a dynamic power. And it is usually greater than the static power. Okay. So static logic means here the static power dissipation is completely eliminated, because here the short circuit power dissipation is completely eliminated, because so during the when the clock is 0, the PMOS will conduct. When the clock is 1, NMOS will conduct. So there is no direct path between the VDD and ground. So therefore short circuit power dissipation is completely eliminated. So, but it has a dynamic power because of this more switching transition, okay, and due to VDD and due to the capacitance, okay. So, on this it is faster. The advantage is it is faster and it consumes less area, okay. So why it is faster means due to less number of transistor, and because of less number of transistor, I have only reduced load capacities, okay, at the output, and due to the absence of short circuit. So during the pre-charge phase, my Y get to VDD. So you can see the TPH L to H. L to H value is 0. So that is also makes this one as faster. Okay, but you have TP HL value. Okay. So since I have used capacitance, periodic refreshing of internal node voltage level of necessary. So let us go to the what are the problem that is associated with dynamic logic. This named as a signal integrity problem. The first one is charge leakage, charge sharing, cascading problem, capacitive clumping, clock feed through, clock mandatory, and output should be valid for the limited period. Okay. So first let us see about the charge leakage problem. The charge leakage problem. Okay, so whenever the clock is 0, the output is charged to VDD. Okay, so whenever the clock is 1, okay, if the clock is 1 and the B value is 0 means, so this NMOS is conducting, but the PMOS is, the NMOS, this one is off. Okay, this is off and this is on. And this is on. Okay, so here the VDD during the pre-charge phase it is charged to VDD. Okay, but it has to remain in the high impedance stage, but this tends to leakage this charge. This leakage in charge is due to first one, since you can see here this P transistor is off. Okay, this is off means what happens when VGS is less than VT. If VGS is less than VT means there won't be any current flow, right? But during the cutoff region, there is a possibility of subthreshold current. Okay, so this I sub, which is very small in magnitude, due to this there is a charge leakage. Okay, due to the subthreshold current of NMOS. Okay, and also you can see due to the here it is in the evaluation phase, so the pre-charge phase is also 0. So this also contribute to the subthreshold current. Okay, So first one is subthreshold current of this is due to NMOS. Okay. So next you can see you have this is N type and this is N type and bulk you have a P type. Okay. So this is NP. So here the I have connected a positive value. So this will leads to a junction reverse leakage current. Okay. So it will flow even when the NMOS is in cutoff region. The similar way you have a for PMOS. Okay, for PMOS you have this is P and this is ground. Okay, so there is a possibility of reverse leakage current. Okay, so here you have a NP. Okay, and you have a reverse leakage current in this direction. So due to this one also, there is a possibility of a reduction in the VDD. Okay. So how to eliminate this one? To eliminate this one, I am going for a bleeder transistor. Bleeder transistor keeper MOS. So whenever the charge get reduced, okay. So if it tends to reduce means the VDD it will goes to inverter and this will make the PMOS turn on. Okay, if the PMOS turn on, the VDD will get charged this capacitor. Okay, by this way I can reduce the charge leakage. Okay, but the one problem is I need to make this W by L ratio of this PMOS is very small. Why? Because if suppose during the evaluation phase if the B is 1, okay, if the B is 1, the charge in the capacitor has to reduce to ground. Okay, so I have to make this this PMOS value as PMOS value W by L ratio smaller. Okay, so this will result in high resistance and it will reduce the static power consumption. So next one is charge sharing problem. Okay, consider during the evaluation phase it get charged to VDD and consider this AB. I have connected ABC. Okay, ABC transistor and AB is on and C is off. Okay, so it will look like this. So initially the charge in the capacitance is VDD. So I can write CL VDD, that is Q of this one is equal to CL F VF plus CL VF plus C2 VF. Okay, so since the charge in the VDD get shared, okay, so it will get shared. Suppose this is 6 means it will get if it is 9, well VDD is 9 means the charge gets shared as 333. Okay, so CL VF plus CL VF plus C1 V2. Okay, so I need to eliminate this problem. So I can write VF is equal to CL divided by CL plus C1 plus C2 into VDD. So okay, in order to avoid this charge sharing problem, I have to make the CL as greater than C1 plus C2. So if it is greater than C1 and C2, so what will happen? VF is equal to CL divided by CL into VDD. So this to get cancelled out, so I will get VDD. So if the C1 get charged to VDD, okay, and VDD, there won't be any charge sharing problem. Okay, so by this way I have reduced the charge sharing problem. Another way to avoid the charge sharing problem is I am going to connect two PMOS at this junction. So whenever the clock is 0 means this VDD get charged this capacitance. Okay, so by this I can avoid the charge sharing problem.